Hello everyone, I'm Shihao Ge from BEM Lab at the School of Computing, Queen's University in Kingston, Canada. Today I will represent my work on developing a scalable framework for multi-level streaming data analytics using deep learning. First, I will talk about the challenges in running deep analytics on streaming data as the motivation behind this research. Then I will talk about the research goal, our proposed solution for a text data analytics use case scenario, validation of our prototype framework with the implementation of a deep learning model, and finally conclude the presentation with a list of future work. Research challenges. Extraction and analysis of information from large-scale streaming data is very challenging and vary for different data domains. For a social media text data analytics use case scenario, the challenges include pre-processing the data, that is tokenization and deduplication of the data, and word or sentence embedding. Data need to be cleaned to remove outliers. The system must be able to handle various data flow volumes. Many traditional machine learning algorithms are iterative and require multiple passes over the data. Some of the complex machine learning processes, such as deep learning, take longer time and cannot be executed within the streaming data analytics pipeline, as it will slow down the processing and choke the pipeline. We need a framework that can perform analytics in multiple levels on the fast-flowing streaming data, on data stored on the disk, and on temporarily held in-memory data for long-running analytics, and also ensure scalability. Our research goal was to develop a multi-level scalable distributed framework to enable effective analysis of streaming data. We explored existing large-scale streaming analytics tools and combined in-memory data structures to enable long-running in-memory analytics and data store for offline data analytics. The usability of the framework is demonstrated using both online and offline data processing and analytics for streaming social media articles, which consists of mainly unstructured text data. The framework is validated by implementing a deep learning model to continuously analyze sentiment of streaming Twitter posts. So this is our proposed framework. It has a data ingestion and processing components, storage components, and this is the offline machine learning components to train models based on stored data offline. And it also has a streaming data analytics component to analyze continuous data strings. And finally, we have decision support components that can generate the decisions. Rather than designing a new tool from scratch, we used an extended open source tools as needed to develop our framework for multi-level analytics of streaming text social media data. So first, for ingesting data stream from their sources such as Twitter into analytics platform and the data store, we are using an integration of NiFi Kafka data flow management tool. NiFi is a real-time integrated data logistics and simple event processing platform, while Kafka is a high-throughput distributed messaging system. NiFi Kafka integration is an open source solution that can provide robustness and scalability as well as the ability to add and remove consumer at any time without changing the data ingestion pipeline. The type of data storage to use in a framework depends on the nature of entities of interest and the target application. So here we select the Hadoop distributed file system, short as HDFS, as the storage system from the available open source solution. HDFS is especially good for storing unstructured data and hybrid data, as it allows data to be stored in a free schema or raw format. It is well suitable for distributed storage processing. It is fault tolerant, scalable, and extremely simple to expand. We also installed Hive and Solr on top of HDFS to extend the offline analytics capabilities. Using historical trader data stored in our framework and an open source machine learning software called Keras, we trained a deep learning model offline and validate the model in the third offline data analytics components here. I will talk about the process later. The offline analytics components also supports other high-level analytics such as SQL query processing with Hive and data indexing and search with Solr. Hive is a data warehouse built on top of the Hadoop ecosystem and is used for data analysis, knowledge organization, and analytical query processing. Solr is a scalable and fault-tolerant platform for distributed data indexing and allow efficient query processing and decision support. Next, we developed the trained model in the streaming data analytics pipeline, which is the fourth component. There are many popular open source distributed streaming data processing and analytics engines such as Apache Spark Streaming and Flink. We used Spark Streaming because it is a fast, in-memory, and distributed data processing engine with elegant and rich development libraries. It can analyze both streaming and non-streaming data and have efficient in-memory data structure that can be used to temporarily hold the data for longer analysis and iterative processing. Spark can also integrate with other deep learning frameworks and incorporate trained models for scoring streaming data. Finally, we're using Zipline and Banana in Solr for decision support. Zipline is a multi-purpose notebook that integrates smoothly with Spark and supports data analytics and visualization with SQL, Scala, and Python. Zipline is used to visualize offline analytics results, and Banana is used to visualize real-time analytics results from Spark streaming via Kafka. We're using a deep learning technique called long short-term memory, short as LSTM, to build a model for computing sentiments in trader streams. LSTM is a gated recurrent neural network that can learn long-term dependency in sequential data. So over here, each single unit of the network takes 3 inputs. xt, the black one over here, is the input of the current time step. ht1, the yellow one beside it, is the output from the previous unit, and CT1, the blue one up there, is the memory of the previous unit. And also, each single unit of the network produces two outputs. HT, which is the orange one, is the output of the current network, whereas the green one, CT, is the memory of the current unit. This single unit makes decision by considering the current input, previous output, and previous memory. And it generates a new output that elicits memory. The network has a sigmoid function for its activation, and its output vector is the forget valve, which is applied to the previous memory CT1 by an element-wise multiplication. These and other features make LSTM a powerful technique for solving sequential and time series related problems. This is the data flow diagram for our project. We created a Twitter data ingestion application using Twitter's developer portal and streaming API to authenticate keys and retrieve Twitter data. Then we created a data flow in NiFi to ingest data streams from the Twitter streaming API. A JSON phraser within NiFi is used to extract the content of the data and then direct the flow into Kafka for distributing data to two channels, one to the HDFS storage and the other one to Solr for search and analytics. The unstructured text Twitter data stored in HDFS can be used for indexing and searching using Solr, and loaded in Hive for further data cleaning, exploration, and visualization in Zipline using the Spark SQL interpreter. This stored data is used to train a sentiment analysis model. The best performing or most accurate model is saved on HDFS and used for real-time sentiment analysis with Spark Streaming to continuously score and assign labels to the incoming tweets from NiFi. Kafka then routes the classified labeled tweets to Solr for real-time visualization of the predicted sentiments. Our project implementation environment is a Hadoop HuntingWorks data platform, short as HDP, developed on the Socic Cloud. It is a cloud-accessible cluster of virtual machines having 48 GB of RAM, 12 vCPU, and 120 GB of memory disk. The software tools we are using are Yarn, Storm, Spark, Zookeeper, Kafka, Zipline Notebook, Solr, HDFS, Hive, HBase on the HDP, and also NiFi and Keras implementation of LSTM. We trained and validated our sentiment classification model using Sentiment 140 Twitter dataset, which started as a class project from the Stanford University and is now available on Kaggle. The datasets contain nearly 1.6 million random tweets labeled as expressing their positive or negative sentiments. Here is the detail about the dataset. The dataset was then uploaded onto HDFS. Once in the system, the data can be explored by Solr and analyzed by Hive, and then loaded in Zipline using the Spark SQL interpreter for visualization, as shown in the screenshot here. This is a screenshot showing detailed information about the LSTM sentiment classification model. We used the Keras implementation of LSTM and the supervised learning approach with labeled data from the Kaggle sentiment 140 dataset, which was split into a 70% training and 30% validation set to train and validate the model. The model parameters were adjusted to improve the model's performance. The first layer of the network is the word embedding layer. It encodes the input data into a sequence of dense vector of 128 dimensions. The next layer is the LSTM layer that transforms the vector sequence into a single vector of size 196 containing information about the entire sequence. Then we have a dense output layer with 2 neurons and a sigmoid activation function to generate a 1 or 0 prediction to indicate a positive or negative sentiment of the tweet. We used log loss as the loss function, which is a binary cross-entropy function in the Keras, and the efficient ADM optimization algorithm. The model was trained for only 8 epochs, as no significant gain in accuracy was observed after 8 epochs. A batch size of 34 tweets was used to space out weight updates while a dropout of 0.2. Parameters such as embed dem, LSTM out, batch size, and dropout are hyperparameters, and their values are learned experimentally. Here's our classification results. We achieved a 82.1% of accuracy for the positive sentiment classes and 79.9% of accuracy for the negative sentiment classes. And overall accuracy is around 80%. This demonstrates that the LSTM models can learn long-term dependency in language. Conclusion and future work. We proposed a distributed multi-level framework for scaling up the analysis of streaming data. We processed streaming unstructured text from Twitter to demonstrate the functionality of our proposed framework. The efficiency of our framework in streaming data analytics is validated by using it to train a deep learning model. Deploying the trained model to predict the sentiments of new incoming tweets, and by enabling querying and visualization of the results. We are working on applying unsupervised learning to streaming data using our framework and developing a real-time model updating approach. Other work involves developing advanced search and analytics strategy using Solr for our industry partner. Thank you very much for your attention. If you have any questions, you can email me at the address given below.